What happens as lakes become anoxic? Does it get worse? Does it improve? Welcome, friends. Jim here. This is a quick video, but I want to discuss something that appeared on phys.org. Anoxia begets anoxia. A positive feedback to the deoxygenation of temperate lakes. So we have a diagram of a temperate lake, in which, starting with the hypolimnetic anoxia, low oxygen level, we have hypolimnetic, and the TP here, as we'll discuss later on, it stands for total phosphate. Then you have epilimnetic total phosphate, epilimnetic chlorophyll A, leading to oxygen demand, leading to hypolimnetic anoxia. Okay, before we go any further, in general, for a typical temperate lake, that's the lake found in mid-latitudes, you have a surface layer called the epilimnion. Then, especially in summer and winter time, you're going to go through a thermocline, and the thermocline tends to be called a metalimnion. And then you have the hypolimnion down at deep depths. Now, a typical temperate lake is what we call dimictic. Mictic refers to mixing schemes. Dimictic means you have two general overturns of the entire water columns in a year. Typically in springtime, with the breakdown of the winter cold surface temperatures, and then in fall with the breakdown after the summer heating. Because summer heating, you get the very warm epilimnion, a pronounced thermocline, and then cooler hypolimnion. That all breaks down. You mix the entire water column, and you get nutrients moved about, oxygen moved about, and so on. You have other types of lakes. You have, for example, amictic, which is no mixings at all. Find such lakes in high polar regions. You have monomictic, which is just one mixing a year. You even have what's called meromictic. Meromictic lakes are lakes where the mixing of the water column is incomplete. It doesn't go all the way down to depth, to the substrate. So you have this permanent anoxic layer at the bottom. And the indications are this is where temperate lakes are heading. By the way, if you want, I did a very lengthy video called, Overturn, Mixing, and Stratification, where I discuss what I just said for the last couple of minutes in gory detail, along with what goes on in the oceans. It's a lengthy video, but if you haven't seen it, or if it's been a while since you've seen it, it'd be worth your while to watch it again, because I explain in detail what I just kind of quickly glossed over. So what is happening here? Anoxia means no oxygen. Hypoxic is low oxygen. Anoxic is no oxygen. Okay? So anoxic conditions are worse than hypoxic conditions, and hypoxic conditions are bad enough. So anoxia threatens inland waters worldwide. Once it has occurred in a lake, the lack of oxygen even sets in motion a downward spiral that accelerates with increasing global warming. Right? Positive feedback loop means run away, not that it's necessarily a good thing. This is indicated by the results of an international study involving researchers at TU Bergakademie, Freiburg, which is published in Global Change Biology. According to the study, lakes that were once affected by a lack of oxygen in deep water are affected again the following year. As a result, the living conditions for fish and invertebrates continue to worsen deteriorate. Greenhouse gases are increasingly released. Nutrient cycles are intensified. So for this study, the international research team analyzed long-term data from more than 600 lakes for the first time, basically in North America and Europe. Based on the data, co-author junior professor Maximilian Lau from TU Berkeley Academy Freiburg concludes, if a lake falls below a critical oxygen content in 1 year, there is a very high probability that it will be affected by even more severe oxygen deficiency in the following year. Although this problematic vicious circle can be deduced from previous knowledge of nutrient dynamics, our team has now been able to decipher the effect of the processes involved for the first time thanks to a large sample size. So they collected more than 100,000 independent measurements campaign, and the study clarifies the reciprocal relationship between water temperature, nutrient retention in the sediment, the development of planktonic algae, and oxygen deficiency. So due to these findings, the team can predict the susceptibility of water bodies to further oxygen crises. The results can now help researchers and authorities to better understand the health of lakes and improve them through targeted nutrient management. New data enables a long-term study. So the long-term data analyzed on the levels of phosphorus, chlorophyll, and oxygen in the water came from 656 lakes, and big collaborative effort. The study team was interested in data from those lakes already showing signs of oxygen depletion. These are often located in the temperate zone of Europe and North America. The data and expertise exchanged with Glion, that's a research group. By working together, we were able to characterize the strength and ubiquity of the oxygen depletion feedback in over 600 lakes on 5 continents, said lead author Abby Lewis from Virginia Tech. So how does it work? In general, rising temperatures favor an extension of the stratification period of lakes and also an intensification of the thermal climate itself. In other words, you have a greater gradient, a sharper gradient, higher temperature difference. During stratification, the exchange of water between warm layers near the surface and deep colder layers is more difficult. Right? You've heard me discuss that before. Climate change is increasing the duration and stability. In other words, this thermal climate is stable for a longer period, which means that the opportunities for mixing is reduced and the time frame for the mixing is reduced. So the climate change is increasing duration and stability of the thermal stratification of lakes, particularly due to the increasingly early onset of spring. This gives the decomposition processes more time to completely use up the limited oxygen supply in the deep water. In addition, rising temperatures favor the increased formation of algae, and then when the algae die, they are decomposed by bacteria at the bottom, which use up the oxygen. That leads to a lack of oxygen in the lake, especially in the deepest parts. Persistent oxygen deficiency leads to the death of almost all higher organisms in the water. Basically, the bacteria are increasing what's called a BOD, the biological oxygen demand, which depletes the oxygen, and then fish and invertebrates such as crayfish and worms and so on, they don't have oxygen. I mean, it's bad enough that normally you get winter fish kill because the lack of oxygen when the lake freezes over, will kill the fish. You're not getting oxygen in there. You're not getting the mixing. No photosynthesis is occurring, so the fish use up the oxygen, and you get winter fish kill. Well, now add insult to injury. You're warming the hell out of the water, and you're increasing the stratification. You're not getting the mixing. It promotes the algae. They die. The bacteria work on them and deplete the oxygen. But what it is pointing out is we're seeing increasing stratification in water systems. Terrestrial, marine, we're just seeing it. And as I said before, when you have increased stratification, yes, stratification is necessary for productivity to take place, but you still need a mixing event. You need a mixing event to turn the water column over, to inject nutrients into the photic zone. With extended stratification, due to increasing warming of the upper layers, you are not going to have that happen. So then what happens? The phytos use up the nutrients. Productivity stops. And if they can't keep increasing their biomass, what are the organisms going to feed on? What are the zooplankton that graze in phytoplankton going to feed on? And then the fish that feed on the zooplankton, etc. What are they going to feed on? You basically have declining secondary productivity that follows the declining primary productivity, and you can then collapse the system. Add in oxygen depletion, so that even if you were to mix the water column, there's no oxygen to mix. And then it's no nutrients to mix. So we're seeing this not just in the ocean, but in lakes. And it's a little easier to document this in lakes because lakes, they tend to be smaller. They tend to be kind of self-contained little systems. But the concept extends everywhere. So this is very concerning. There's a lot of temperate lakes, we have prize fishes in them, be it bass, trout, right, pike. So this is yet another consequence of what increasing temperatures are doing to the planet. Thank you for your time.